Hi, everybody. So my name's Mark. This is really, really comfy. I'm really happy about this. I think this is one of the first times I've given a talk on something so nice. Okay, so I work at Akamai, and in my industry, we say I wear many hats. I am an employee of Akamai, but I also am the working group chair of the HTTPbis Working Group in the IETF. The IETF is the organization that's brought us protocols like TCP and IP and HTTP and what have you. I do stuff in the W3C as well and other places. Tonight, I'm going to be talking mostly with that IETF working group chair hat on and talking from that perspective. I can give an Akamai perspective on this stuff too if you want to ask questions about that, but that's kind of the angle for this. And so HTTPbis is the working group that I chair. It is the working group that is effectively in charge of the HTTP protocol. We convened it first. The original HTTP working group worked in the 90s to do HTTP 1.1 and to document 1.0. And we'd started HTTPbis in about 2007-ish. And we did that to revise RFC 2616, the specification of HTTP 1.1, because we realized there were a lot of holes and inconsistencies and areas that needed clarification in that spec. It's a pretty obtuse spec. And what happened was I and Roy Fielding and Julian Reschke and other HTTP experts kept on getting asked questions of interpretation of the spec again and again and again. So we decided to write it down again more clearly so we had a better document for the community. And we started that in 2007, and we are literally finishing right now. There should be new RFCs replacing RFC 2616 within, I'd say, the next week. Probably shorter than that, which is very exciting because that's a big chunk of our lives. And it's been split up into 6 different documents, so it's a little easier to navigate because RFCs are still just ASCII text documents. So when those come out, let's say in the next week, please have a look. Please use those instead of RFC 2616. Hopefully they'll be a lot more clear and useful to developers. And so in the process of doing that, one of the things when we set up the working group, we said, we're not going to do a new version of HTTP. This is just going to be redocumenting HTTP 1.1 because there's no support for doing a new version of HTTP. We don't have the right people here. We don't have implementer interest. And so we're not going to do that. And we put that in our charter. And then in 2009, Google started making some noise about Speedy. And we heard about that, and we changed our minds. And what has eventuated, and what I'm going to talk about tonight, is HTTP 2. The working group was rechartered to work on that. And so when I talk about HTTP 2, usually the first question that people ask is why are we changing HTTP? Why are we making backwards incompatible changes to the wire format of what is arguably the most popular and widely used application protocol on the internet? You know, it's a pretty big deal. And there are a lot of answers to that, but one of the most important ones, I think, is that the web itself has changed, and how we use the web has changed quite a bit since Tim and Roy and a couple other people wrote down, you know, became HTTP 0.9 way back in the early 90s. And there are a couple of things that have changed. Excuse me. One is that the web has become a lot heavier and more interactive in those intervening 15, 20 years. This is a slide or a chart from the HTTP archive by Steve Souders. I trust you all know who Steve is. Saint Steve, perhaps. And it shows total transfer size and requests for web pages. This is from the Alexa Top 1000 and over a 4-year period. So you can see 4 years ago, an average page was something like 600K. But these days, it's more like 1.5 megabytes, which is a lot of data. I mean, that wouldn't fit on a floppy disk, which kind of probably tells you how old I am. Likewise, number of requests, you know, started in the 70s and 80s per page, requests per page. And now we're north of 100 requests per page. And that's a little flatter, which is an interesting story in itself. But, you know, the big story here is we have a lot more going on when you're loading a web page. Not only is there a lot more being downloaded and a lot more requests being made, but it's more interactive. We're using a lot more AJAX and other things that are much chattier with the server. At the same time, I think the industry has come to a place, and I'm sure everyone here is aware of this, where we've got a direct correlation between web performance and end users' attention and therefore revenue. Therefore, you know, whatever the good metrics we have to measure how successful our websites are. You know, this is a study from Bing showing that if they added delay to responses, lots of important metrics go south. Revenue per visitor, clicks, satisfaction, user satisfaction as they measure it. And this isn't just Microsoft. Google's done these studies, Amazon's done these studies. Most big websites have made this correlation pretty strongly, and kind of why we're all here. Finally, and by the way, that slide and this slide are both from Ilya Grigoryk's Web Perf crash course presentation. If you haven't seen that, I've got a link at the end. It's a great presentation. You talk about a new book for HTTP. I think Ilya probably will do that. He seems to be able to write them pretty quick. Mobile is the other factor. We're living in a world where a lot of websites and a lot of end users are in a mobile-first kind of mindset, or mobile only, where they're going and using the web on mobile devices exclusively because of economics or because of where they live or because of convenience. And the problem is mobile has a very different behavior from a performance perspective. So for example, we're doing some experimentation with the Sprint networks in the US, showing that on a 4G network, they were seeing an average latency of 150 milliseconds, and that's inside the US. On a 3G network, you're seeing more like 400 milliseconds, and 3G is still pretty common, of course. So I live in Australia, and my usual latency to the US is something like 200, 250 milliseconds, which means that on a mobile network in the US, you're seeing worse performance often than I'll see halfway around the world. So it has a lot of impact on performance. And that's because of how mobile works. It's how the radios are managed and so forth. And so what we have is a lot of what happens in web engineering today, you have neat little tricks that developers play to get the most out of performance in HTTP. So for example, a very common technique these days is spriting, where you have, instead of having 50 or 100 different little image downloads, you make it all one image, and then you use CSS to create a window over that. This is Google, Sprite, Facebook. I think the third one's going to be Amazon, and the fourth one is eBay. And it's a very common technique. I think most people are familiar with this. It helps you avoid making extra requests. But it comes with some problems. You have to integrate spriting into your workflow to get it onto the site. And if you just want to change one of those little images, even just a couple of pixels, you have to invalidate the entire thing in your cache and re-download it to the device, which over a limited network can be non-trivial. Another technique that's becoming pretty popular is inlining, where you make a decision to inline an image, for example, instead of downloading it as a separate resource again. So this is an example from the Apple homepage. And what I find interesting about this slide is, there was an engineer at Apple who made an informed judgment that it was better to inline this image as a data URI, even though it's base64 encoded, and there's also some percent encoding in here. And you can see it goes on for a fair ways. I mean, that's a lot of bloat on the image, because it has to be textual rather than binary. But they decided that would give them better performance. So that's an interesting decision. Another common technique is sharding, where you're trying to overcome the limitations on connections in the browser. And so you use different host names to download your images. This is YouTube sharding a picture of Tim Minchin. And finally, concatenation is another kind of industry best practice, where you're using, you're concatenating your JavaScript and your CSS, each of them into one file, so that you're avoiding having, modular separate downloads and more granular downloads. And I consider all of these hacks, and I mean that in a complimentary fashion. A hack is where an engineer is going and creatively working around a problem by using a system in a way that it wasn't intended. They're addressing a problem and doing something a little bit creative, and that's cool. But when you have a lot of hacks, to me, it's a sign that there are problems in the underlying system. And if you can fix the underlying system, if you can make it so people don't have to hack around those problems, you're making it better for everyone. You make it so people don't have to do hacks. And you're making it so that you can improve performance, in this case, for cases where they can't hack around those characteristics of the system. So it's pressure, it's indication of pressure that you need to change HTTP in this case. And the mantra that you hear so often in the performance industry, as personified by Steve here, is eliminate requests. You hear this at all the conferences, at Velocity and at the meetups and so forth, and in the books. We need to eliminate requests and reduce the number of requests you make on a page. And those techniques that I was talking about, a lot of them are about how do I eliminate requests. And so when that becomes apparent, the first and most obvious question is, why are these requests so expensive? What can we do to minimize that overhead? There are a couple of reasons in HTTP 1. One is that HTTP 1 uses TCP, the underlying transport protocol, really poorly. So this is a visualization of a page load, or the start of a page load, I should say, using a tool I wrote a while back called htracer. It's just a bit of Node. And what it does is it uses PCAP and listens to what happens in the wire and then recreates what you're doing with TCP as well as HTTP and visualizes it. So here, each of the horizontal gray bars, they're a bit dark, represents one TCP connection to a server. And the red dots on the tops of the bars is an HTTP request, and the red lines on the bottoms of the bars are the corresponding responses. The individual white lines on the bars are the actual TCP packets flowing in each direction. So you can see, you make a request, you wait a round trip, you start getting the response. That's the HTML coming down there on the top. The browser eventually gets the HTML and can parse it and can start issuing requests. It opens some connections. And you see here there are a lot of parallel connections to the same server. We send out one request on each one. We wait a round trip, and then we start getting a response. And once the response is complete, we send another request. And you can see there's very inefficient use of the TCP connections here. And that's because of a phenomenon in HTTP called head-of-line blocking. This is where effectively you can only have one outstanding request per connection. And that's because in HTTP 1, the relationship between the request message and the response message is implicit. There's nothing explicit saying, I'm the response to that request. You have to keep an ordering of each of the request and responses seen and say, okay, this is the response to that request because it's the nth one, and that was the nth request. And even HTTP 1.1 tried to address that a little bit by introducing what's called pipelining, where you can say, okay, here's request A, B, C, D, and we know that the responses are going to come in the same order on the wire. But even when you do that, a big or a slow response, let's say it takes a long time to generate on the server or it's really big to download, in either case can block all the responses behind it. There are also practical issues with pipelining. It's very difficult to use pipelining as a client because of a lot of weird behaviors on the internet. As a result of this, the state-of-the-art in web browsers is you only use 4 to 8 connections to a web server at a time. That's how you get parallelism. You put all your requests on between 4 and 8 connections. Now, as a result, HTTP flows tend to be really short and bursty. You open these connections, you use them for a couple of requests. They're hot, then they're cold, then you shut them down, you open more connections. And short and bursty connections are exactly what TCP is not engineered for. TCP as a protocol is optimized for very long-lived, heavily used flows. Originally it's for downloading. Still working? Okay. Downloading things. So we're not using TCP optimally. There's also an interaction with TCP congestion control. So for example, in TCP slow start, when you open up a connection, you don't immediately blat bits down that connection, because if you do, if you're doing that into a congested or a limited network, you can cause more problems than you're solving. It's great for performance to immediately utilize all of that connection if it's a really heavy connection, but if it's congested, you actually create more problems because, for example, if you overflow all the buffers in one of the middle boxes along the way, one of the routers, they'll drop packets on the floor, and then you have to retransmit, and you add artificial delay. And this is actually, this phenomenon is why browsers don't use, let's say, 100 connections to download a page. Because if you use 100 connections to download a page, it's very likely you'll create congestion events on that network, and therefore you'll have worse performance overall. That's why they've settled on between 4 and 8. And so TCP slow start is bad for performance in that when you originally set up a connection, you're not getting the full utilization of that connection. But it's good for performance because congestion control is your friend. You do need it. Otherwise, you have an overloaded network. But this is one of the reasons why it's important to have a long-lived flow in TCP rather than a short flow. And so we're at this state now where HTTP is using multiple connections for parallelism. And that increases the chances of congestion events. You imagine you're doing a page load with those 100 assets, and let's say you're doing it across 5 or 10 different origins. That means you have something between 20 and 80 connections open to different servers. And if you're on a limited network, that can get really bad really quickly. There's a phenomenon called buffer bloat that makes that worse. I won't go into that too deeply right now. It's also resource intensive on servers. You have to keep more sockets open. But most importantly to me, all of this is really tricky for clients to manage. If you think about it, to do a page load, I've got to download, let's say, 100 different assets. And I've only got 4 to 8 connections to do it over on, if it's one server. I've got to decide which requests to make on which connection and in what order and when to get the most optimal performance possible. Because if any one of those requests blocks on the origin server or it's really slow to download, everything behind it has to wait. You have to queue a lot of stuff. And so the browsers end up using a mess of heuristics to figure this out. They have to guess. They have to say, okay, I'm going to download the CSS on that connection and the JavaScript over here, and I'm going to hope that that's a reasonable thing to do, and these images and those images and so forth and so on. And a lot of the time they get it right. I mean, they've done a lot of refinement over the years. These guys use a lot of data to make their decisions. They're really good at it. But at the end of the day, they're still guessing, and they don't want to be able to, they don't want to have to do that. Excuse me. Another factor that makes requests expensive in HTTP1 is that HTTP headers are verbose. There's a lot of them on the wire. So just to give an example, this is a page load for Etsy.com, and I'm going to show you the first 4 requests. There are many more, but I'll show you the first 4 requests on just one of the connections the browser used to download Etsy. And so here's your first request, 525 bytes, HTML request for the root document. Pretty vanilla stuff. Don't worry, that's not my password. 525 bytes, great. Second request on the same page, we're downloading some JavaScript. And it's a bit bigger because I think we've got a bit of bigger cookie and the URL's a bit bigger, and all of a sudden we've had a refer header pop up. But there's something interesting here. There are 690 bytes in this request in total, but only 226 are different from the last request. Everything else is, the user agent's going to be the same. The host is the same. Connection keep alive, accept encoding, so forth. It's just the new refer because now we have one. The accept header is different because we're doing a JavaScript download. Of course, the URL is different. And the cookie has been updated by the HTML response, we assume. Third request, things get interesting. Still about the same size, 683 bytes. But look what's happened. We're doing another JavaScript download, and we've gone into a steady state. The refer is the same, accept is the same user agent, the cookie settled down. There's only 14 new bytes here, and that's just because the URL's changed a little bit. Everything else is the same. Last request for our purposes, same thing. Almost the same number of bytes, 698, only 28 new bytes. That's, not a lot of new information for so much on the wire. And this is important. We've got 4 requests. They represent almost 2,600 bytes. That means at least 3 packets on most networks because of the way that TCP and IP work. But almost 1,800 of those bytes were redundant. And it's important because it's something I like to illustrate is what I call Patrick's test. So Patrick McManus is the lead network engineer for Mozilla. And he came and illustrated to the working group why this is important. If you think about a page load that has 83 assets, and that's conservative as we saw from the HTTP archive numbers. If it has 83 assets to download on a connection, and the initial congestion window is 3, and let's imagine you have 1,400 bytes of headers, which is not that uncommon these days with cookies and URIs and refers and so forth. That means that just to get those requests out on the wire, I'm not talking about getting responses back or anything, I'm just talking because of the way that TCP and IP work, and you have to start, with TCP slow start, and you have to wait those round trips. It's 7 to 8 round trips just to get the requests out on the wire. Now you think about that in a mobile context, where your latency might be something like 400 milliseconds for each of those round trips, and you start to understand why web performance can suck in some states. So this is really important. These headers have an impact on web performance. Response headers, not so much, because they're dwarfed by most of the payloads you're working with. But for requests, just getting the request to the server, it adds a lot of overhead. So what are we doing about all of this in HTTP 2? The first thing to say, Speedy was the starting point for HTTP 2. We used that as the starting point for our protocol because it was available and because Mike and Roberto brought it to the group. Mike Belshi and Roberto Pion are both Google employees that did Speedy on their 20% time. And they brought it to the group as a proposal for HTTP 2 when we asked for it. And Mike and Roberto will be the first people to say, we're not doing anything new here. This is not rocket science. All the techniques that we talk about and that we're using have been talked about before. There have been multiple proposals for HTTP replacement. One was Opera Turbo. They had their own little protocol that they used to their own proxies for a while. I don't know if they're still doing that or not. That's a good question. HTTPNG was similar in some ways. That was an effort in the W3C way back in about 2000, I think. And Waka was an HTTP replacement protocol that Roy Fielding was working on for a long time. Unfortunately, he never wrote it down, so we can't use that as the basis of the work. But there's nothing new here. What's new is that we have implementers in the room working together to actually ship a protocol in product, and that's what you need to do standards work. It doesn't do anybody any good if it's theoretical. So this is a snippet from our charter. The high points are, we need to improve end-user perceived latency, address that header-line blocking problem I talked about, improve the use of TCP. There's a bunch more, but that's the high points. The underlying goal is that we want to be able to use one TCP connection to do a page load. Not that we require that, but that's a goal that browsers should be able to do that. And that's their stated intention so far. They want to use one connection at a time per origin. And that's because, like I said, TCP likes these longer-lived flows. It's less resource intensive on the server especially. And it's more fair. TCP has this notion, and the internet has this notion baked into it of fairness, that one application shouldn't steal more resources than are its share. So if I'm at home and I'm browsing the web or doing a download with my browser, and my wife is on a VoIP call, neither application should overcome the other one. They should be able to share those resources adequately. And when HTTP uses so many connections, it actually hurts the fairness of the internet. And so we're doing this. The first thing that you do in this is we're separating the semantics from framing. And what I mean by that, in an HTTP1 message, most of the headers have to do with the payload. Most of them have to do with actually the semantics of what you're talking about in the request or the response. But some of them are more about the framing. They're more about how do I tell where this message stops and the next one starts. So here, for example, transfer encoding and connection talk about the framing of the message more than really about how it's put on the wire, rather than about the long-term semantics of it. Content length is like that as well, keep alive as well. In HTTP2, we've gone to a binary format. And the fundamental unit is what we call a frame. And a frame is just a little carrier for data. It has a length field to tell you how long the payload is. It has a type field to tell you what kind of frame it is, and I'll talk about those in a second. It has some type-specific flags. And then it has a stream ID. And the stream ID is a 31-bit identifier that tells you what stream this is associated with in the connection. And we use streams to compose HTTP request-response interactions. So the frame types, there are a bunch more, but these are kind of the big ones. Settings talks about the overall connection. It allows you to say, okay, here is the state of this connection, and these are parameters for the connection overall, rather than for any particular message. Headers and data can be used to compose actual HTTP messages, and I'll illustrate that in a second. And reset stream and go away allow you to manipulate the state of individual streams and connections. Reset stream says, I want this stream to go away. And go away says, I want the entire connection to go away gracefully. So you can shut down a connection gracefully rather than rudely cutting it off like you do in HTTP1. So you can use these primitives to recreate HTTP messages. Here, for example, you have an HTTP request on the top, and it's just composed of a headers frame because if it's a GET request, it's not going to have a body. And then a response is a headers frame and a bunch of data frames in this case. You can use multiple headers frames, or actually have a separate continuation frame if the headers are really big. And you can use multiple data frames to spread it out. And once you do this, once you chop up your HTTP messages into these little primitives, you can then do multiplexing. You can mix and match lots of different HTTP request response interactions on one connection at the same time. Because remember, you've got that stream identifier that lets you tie them together explicitly and say this is part of request number 1 and this is part of response number 1 and so forth and so on. And so you can interleave headers and data frames from different kinds of requests and responses at the same time on the wire and not worry about them blocking each other. You get that full multiplexing, which is getting around that head of line blocking problem I talked about. When you have multiplexing, there are two things that come along with that you need. One is prioritization. And this is the notion that if naively a browser, once you have multiplexing, could just say, okay, I need to download 100 assets. Here's 100 things, give them all to me. And naively a server would say, okay, I'll give them all to you at the same time. I'll evenly parse them out, or I'll send them to you in order or whatever. But that's not good for performance. The browser needs different things at different times to get the optimal page load. You need your CSS and your JavaScript before you need your images usually, so you can tell how to lay out the page. And so prioritization allows the client, the browser usually, to give hints to the server and says, I need that one first, or this thing depends on that thing. And prioritization has been shown by everyone's experimentation to be really important for performance and speedy in HTTP2. It also lets you do cool things like, for example, let's say a browser has 10 tabs open to a website, all to the same website, and the user is on tab 3, and then they click on tab 7. Reprioritization allows you to say, you know what, downgrade those things on tab 3. I need the stuff on tab 7 now, and to make those more important in the download so the server can respect that, and you can get better performance on that tab. Or if things are below the page fold and then they come into the viewport and everything's still downloading, you can prioritize the stuff that's come into the viewport, for example. Flow control is simply being able, like all kinds of flow control, being able to manage your buffers so that you've got to have all this stuff being shoved at you, whether you're handling requests or responses. You've got all this data being shoved at you. You want to be able to manage how much of it you have to buffer if you're consuming it at a slower pace. This is especially important for intermediaries. If you're not an intermediary, you might not have to pay attention to flow control so much. The other big thing that's being done is header compression to get around that verbosity we talked about. So Speedy 2 and the first versions we worked with used gzip to do this. And Mike and Roberta did something really clever in Speedy with compression. They used gzip, and you used the same gzip context for all messages in one direction on a connection. So you have one gzip context for requests on the connection and another one for responses. And when you do that, it has a really interesting property. Let's imagine, the first message on the connection is, let's say, 2K, just for the request headers. It's a really big request header for some reason. And let's say that gzips down to, let's say, 500 bytes. So you get some compression benefits. That's great. But because you've preceded the compression context with that first message, and that's effectively forming part of the dictionary, the compression dictionary, the second message on the wire, the second request, compresses down to something like 10 or 12 bytes. And that's because those messages are so similar. There's so much repeated data. As we saw before with Etsy, there's so much repeated data, you get these ridiculous efficiencies in compression. And when I talked about Patrick's test before, those 83 messages that you had to take 7 to 8 round trips to serialize out on the wire. When you use gzip on those, for example, they compress down to 1 round trip and maybe even 1 packet. So it's a huge advantage for performance. It's very efficient. It's easy to implement. Everybody understands gzip. We know we've got a library for it. That's great. There was some concern about memory overhead around using gzip because especially if you're a proxy and you have to maintain a gzip context for one for each direction for every connection you hold, that can be very memory hungry. But we were talking about ways around that. But a much bigger concern came to light, which is an attack called crime. The security guys found this. And basically, crime is when you're doing encryption and you're doing compression inside that encryption, and an attacker has the ability to inject data into that stream, into that compressed stream. And since this is the web and we've got JavaScript, it's pretty easy for attackers to inject data. You just, find a way to get the user to go to a website while they're going to another website and inject requests, and off you go. When you have that ability, you can actually recover the plain text. You might have to make millions of requests, but you can probe the key space. You can say, okay, if there's a secret in there, A, B, C, D, E, F, G, H, I, and the attacker sends ABC, and they can observe the compressed and encrypted ciphertext getting smaller, they know that ABC is inside there. And then they can probe the next bit and the next bit and reassemble your secret. This is actually demonstrated. They showed people recovering authentication tokens and cookies. And so the security guys waved their hands and said, no, you can't do this. It's not good enough. So we couldn't use gzip. And we went off and we asked for proposals, and we had a bunch. And what we've ended up with is called HPACK, which is effectively what you can think of it as coarse-grained delta coding. It allows you to remember what headers you've seen on a connection in one direction and say, and refer to them, do it by reference rather than doing a literal value. You can say, use the header that you stored back then, and so repeat this header value. But it's at the granularity of an entire header value. And so an attacker can't search the key space incrementally. They have to guess an entire header value at one time to be able to recover a plain text. And so we went back and forth on this. The security guy thinks it's good enough. There are some concerns that if you have a really low entropy secret, you have a really dumb password, for example, and that's alone in a header value, it can still be guessed. But it's an acceptable risk, most people think. And in fact, we get pretty good compression with this approach. We put together a test bed to judge all the different proposals we got, and we got a header corpus. This is all the requests to do, request headers to do 4 page loads, I think, on Amazon.com. And you can see the blue line is the HTTP 1.1 header sizes. So there are more than 350 requests in total. There are a bunch around 14 and 1600 bytes, and a bunch around 600 bytes, and a few less, and a few more. And you can see the orange line, gzip, that's the Speedy 2, Speedy 3 approach. Gzip gives you really good compression. A lot of them are less than 50 bytes. But the green line is the HPACK approach, using the much coarser granularity. And you can see it, with a few exceptions, it gets really close to the gzip approach, but it's much safer. And so we're pretty happy with this, in that it's pretty secure, we think. We've had a lot of security review of it. It gets decent efficiency. There are some complaints about complexity, in that you have to go off and implement this new compression algorithm. You have to do Huffman encoding. A lot of developers aren't as familiar with Huffman encoding. We're hoping good libraries for this will come out because, gzip itself is quite complex, but nobody thinks of it as complex because it's all hidden under the covers. Hopefully the same will happen with HPACK. The other thing that's happening is server push. And this is merely the observation that if you think about it, when you do a page load, there's a bit of a wasted round trip, potentially. You go off and you get some HTML, and you send that back to the browser, and the browser does the parse on the HTML and grabs a bunch of links out and makes those requests, and you get those responses. But the server just sent that HTML. It knows what's in that HTML. It knows that you're probably going to need these images and that JavaScript and that CSS. So why does it have to wait that round trip to send those things? And server push is merely the server sending something along with an HTML response that says, I think you're going to need this. What you're effectively doing from an HTTP standpoint is pushing a synthetic request and response pair into the cache of the client so the client can use that optimistically. Now, it could be that the client already has that thing in its cache. That's kind of the first obvious observation you can make there. And in HTTP2, we have an answer for that. If the client already has it or if it doesn't need it, you can use that reset stream frame. And you can say, I don't need this stream, throw it away. And so when somebody starts pushing you something, you reset the stream if you don't need it, and you don't have to worry about that. And so you lose a little bit of bandwidth potential in that first round trip, but you can cap that loss. If the client really, really doesn't want server push, you can actually turn off the mechanism altogether in the protocol when it opens the connection. And so that's kind of a way to save a round trip. I think server push is probably one of the more experimental parts of the protocol. The community doesn't have a lot of experience with this yet because it requires people to rethink their stack and figure out how to integrate the concept of push into their apps. But there's a lot of potential performance win there. And another observation that often comes up about server push is that we kind of already have it in that we have CSS inlining. You can already inline. You can force something down the throat of a client. You can inline an image, and they don't have a choice about whether they get that image or not. But here we're hoping we have a bit more granularity and a little more control with server push. So where are we now? Google announced Speedy in late 2009, and then they went through a quiet period for a while. Mike came and presented what they were doing to us in the HTTP Working Group in IETF 80 in early 2000, I think March 2011, maybe April. And that was good. That was nice to get that shot across the bow. Things got more interesting in 2012. Firefox shipped Speedy early on in the year. And after that, we saw a lot of buzz in the community and a lot of interest in Speedy. And we kind of made a conscious decision that as a standards community, we could either let this happen and let Google own it and let them kind of make it a proprietary HTTP replacement, or we could take it on as a community and allow all the stakeholders to come to the table and figure out what we want out of this thing. And I saw enough interest from HTTP implementers to make me believe we could be successful in doing that. If it were an academic exercise or we had, we didn't have the right people at the table, I don't think we would be doing this now. But we had a good representation of HTTP implementers there. So what we did was we made a call for proposals. We said, as a community, we're thinking about the next version of HTTP. We'd like to hear people's proposals. We got 3 proposals. By far, Speedy was the most complete and broadly supported. And so it was kind of a no-brainer to choose that as the basis for the work. And so we took a copy of the Speedy document and called that Draft 00 and started iterating on that and figuring out what we wanted to keep and throw away and evolve. And that was rechartered in kind of I think it was like August, September 2012. And what I like to point out here is that we kind of caught it early. Netcraft started doing a survey of Speedy servers on the net. And at that time, I think that was about June or so of 2012, they saw 338 Speedy servers. So it wasn't yet widely deployed. We had a chance to get early in the curve. And that's important to me because it's not interesting just to rubber stamp somebody else's spec. We really wanted to make sure we got good community input there. And so after that, we started a heartbeat where we published drafts quite often. And every once in a while, we would mark one of those drafts as an implementation draft. It's a way of saying we want the community to go out and implement this thing and come together and have an interop session so we can figure out what works and what doesn't and get feedback on how to evolve the protocol. Okay, it's still working. And so we had our first implementation draft after we met in San Francisco at Twitter, and we decided to do the first implementation draft right after that. And then we had, not that long afterwards, it was probably 4, maybe 6 weeks afterwards, we had a face-to-face meeting in Hamburg. And we said, everybody bring your implementations, let's see how this thing works. And I was really hoping, it was a really short amount of time, I was hoping we'd have maybe 3 show up. We ended up having 10 show up. And we demonstrated interop on the first day, which to me was a really good sign that we were onto something. We had a really good selection of clients. We did another implementation draft after that meeting. Met again in Seattle, did draft 9, another one. Had a couple meetings early this year. And our most recent implementation draft is draft 12. We're here this week in New York to talk about that. And we're starting to really talk about, let's ship this thing, let's get it done. And the reason for that is that if, this could very easily become a 5-year effort if we let it. It's very easy for standards efforts to go on and on and on. But when you do that, they tend to become more research projects and academic projects than actual live code. I'm very conscious that if this thing takes too long, I'm going to lose the interest of all the browser vendors and all the server-side guys and the CDN folks and the load balancer folks who are putting a lot of engineering effort into this. And if we lose their interest, we lose touch with the reality. So we can't let that happen. Our current implementation list, I've pruned a couple off of this because some people haven't caught up. But we've got good representation for this latest draft. Netty is probably our most recent implementation to join us in Java. NGHTTP2 is in C. It's actually a really good implementation. And that's come out of the Japanese community. We've got a lot of Japanese folks participating and implementing, which is great. Katana is the Microsoft open source implementation, completely separate from Microsoft, but Microsoft is there too. Node.js, we have a Node HTTP2 coming again out of the Japanese community. We've got Mozilla, Akamai is implementing, Chrome is implementing. Twitter is implementing in Java, and they have shipped every one of our implementation drafts live on all the Twitter sites. So you can go today to Twitter and negotiate for draft 12, which is crazy, but that's how those guys do it. So good for them. They like living on the bleeding edge. We've got a Wireshark plugin. There's Go. OKHTTP is from Square. Ruby, Python, and curl is now on board. Daniel Stenberg has integrated one of the HTTP2 libraries into curl so you can use it as a command line client, which is great to see a non-browser client out there as well. How will it affect web ops and web developers? So the first thing is it'll be easier to go fast, and there's some nuance to this. It's not a magic button. HTTP2 doesn't magically make your website 50% faster, no matter what anyone's going to tell you. The anecdotal evidence is that by deploying it, as long as you make some sensible decisions about deploying it, you can easily see somewhere between a 5 and 15% performance gain. But that's an average. That's not for every scenario. there are cases where you're actually going to see worse performance for right now, and a lot of that has to do with how it interacts with TCP. I'll talk about that in a little while. But it does, I like to say it unblocks performance. It gets these nasty things like head-of-line blocking and really big headers out of the way of performance, and it enables you to see better performance in the long run. Some numbers from Google they released, these are regarding Speedy 3, which is effectively HTTP 2. Median improvement on Google News was 43%. For slow connections, their 95th percentile, it's 44%, which is good. Not quite as much on something like Google Maps and Google Drive, but you get a sense, these are very highly tuned, of course, but those are the numbers that they're seeing. Twitter is a different case. This is a non-browser case. When you use Twitter on a normal, like on your mobile client, the standalone clients, they're using Speedy in the background to do all their fetching. And these are the numbers they see for raw request latency, so you can see they're getting improvement between HTTP 2 and Speedy, especially when there's a lot of latency, which is good to see. And this is a way that I think is really useful to visualize the difference in the protocol. This is a page load, I think, for Wikipedia. And you can see on the top the HTTP 1.1 approach, where you get the HTML and you get the JavaScript, you get the CSS, and then you get all your images, but there are a whole bunch of them that are blocked. You get that beige, the dreaded beige bit, where the images are blocked because there are no available connections for them. And that doesn't happen in Speedy and HTTP 2 because you have multiplexing. You can get them all down and get them all started immediately. And you share those resources, and so you get much quicker time to completion. Probably one of the more extreme versions of this that I saw when I was at Yahoo. We were debugging performance on a property, and you're doing page loads across the Pacific. I think it was one of the Asian properties, and we were debugging it from San Francisco. And they were downloading something like 150 images for the page load, and so you saw this really painful stair step of 4 images downloading, then 4 more, then 4 more, then 4 more. And it just gets really painful really quickly. So the idea is to avoid that here. Really important thing to note, the idea here is we're not changing the semantics of HTTP. We're not doing this to introduce new headers or methods or status codes or change how you use HTTP. You should be able to use the same HTTP APIs that you use for HTTP 1.1. They might have a couple of new knobs on them to adjust things and optimize, but the core, request method, status code, headers, that sort of stuff should be exactly the same API. Having said that, because we're radically changing how HTTP uses the underlying transport, TCP, how it behaves is going to change. In protocols, we have these things called leaky abstractions, where, no matter how much we want to say, I'm using HTTP, I'm not using stuff below it, I can ignore the stuff below it. The fact is, once you change how it uses TCP, those changes leak up in the behavior of the protocol. And so, for example, you don't do the inlining anymore, you don't do spreading or concatenation because you don't need to, and the behavior changes. Another behavioral change because of this is connection handling. These connections are going to be much longer lived, and that changes how you think about load balancing and failover. And we actually have a couple of new facilities in HTTP 2 that have been added more recently to help with this. One is called alternative services, and this is the notion that if you've got a connection open to me, and I'm a server, and I need to load balance you or fail you over to some other server, I can send something to you that says, please use that server over there and stop using me once you have a connection to him open. And so have a graceful transfer once the connection's open and set up, but make that transparent to the end user so it still looks like they're going to the same origin. It's kind of a redirect, but it's kind of like almost a CNAME at an HTTP level. And it gives you the ability to shift traffic around a lot more seamlessly and with a lot more control than using DNS or other techniques. You'll probably have to use TLS from the look of things. We've talked long and hard, and one of the most contentious issues in the working group has been about security. And we've made a decision in the working group not to require the use of TLS for the new protocol. However, some implementations, especially Firefox and Chrome, have publicly stated that they are going to require the use of TLS. They have a couple of different techniques for that, but they require TLS to use the new protocol. And they're trying to incent better security on the web. Part of that is Snowden. Part of that is stuff that predates Snowden. It's stuff like Google Street View when they were driving around Germany and sniffing up people's passwords. or the Firesheep attack, where you could install a Firefox extension and sniff people's passwords off of your local coffee shop Wi-Fi. The browser guys really keenly feel that they own, they need to own end-user security, and they need to improve the level of security in the web, and that's one of the reasons they're doing this. Another reason is when you deploy a new protocol on the web as big as HTTP, middle boxes, the proxies and the transparent proxies and firewalls and so forth, like to do things to HTTP, assuming it's going to be HTTP 1.1. And so when you try and change and evolve the protocol, it breaks a lot of things. If you encrypt it, you don't have to worry about that so much. So that's part of the discussion, and there's an ongoing discussion there, which is quite interesting. Another thing that's going to change for folks is debugging the protocol. It's a binary format now. We do have a Wireshark plugin that makes it easier to use. I'm hoping more tools are going to emerge from the community, but you can no longer just telnet to a server and type in get, as I still love to do. It's a bit of a loss, but I think it's an important gain. A binary protocol is a big win in a number of ways. Yes, it's more efficient on the wire. Yes, it's more efficient to parse, so you can scale out servers better. But more importantly, it's much more precise. Textual protocols are very error-prone because you have to think about things like white space handling, and you have to think about things like new lines and how to convert those. And you have to think about, okay, I have to sling these strings around and compare them a lot. It's very inefficient and you have to have a lot of error handling in your code. And in fact, in HTTP 1.1, it's a perfect example. There are 4 different ways to parse an HTTP message in HTTP 1.1. You've got connection close, you've got content length, you've got transfer encoding, and then you've got the special multi-part MIME type. And so the code is it's all over the place, and there are lots of special cases, and we've seen a number of bugs and a lot of security-sensitive bugs over the years caused by the complexity of HTTP message parsing. With a binary format, all of that goes away. It becomes much simpler and much more robust. Right before they announced Speedy 2 to the world, Mike Belshie invited me out to dinner and told me what they were doing. And I went home, and in 3 days, I took one of my existing HTTP implementations in Python and rewrote, using the same API, I switched out under the covers and did what has become HTTP 2. Sorry, I keep on saying HTTP 2 because I've trained myself not to say Speedy. But what was amazing to me about that experience was the HTTP 1 code was, pages of handling all the different cases and slinging strings around and lots of copying. And the code for parsing Speedy 2 was really compact, really elegant, very performant. I knew that it worked because when it doesn't work, it breaks horribly. And so it's very robust. I really liked it. And that's important for protocols. Getting the absolute most in performance is going to take some effort. It's the stated goal of the working group, and it's a goal for me that this thing needs to ship and out of the box be performant, especially for open source implementations. And we're working on best practices and stuff like that to make sure that happens. But to get the absolute, we want it to ship and be better than HTTP 1. But to get the most out of the protocol, you're going to need to make decisions like when do I do server push, and how do I handle prioritization and stuff like that. And so there's going to be tweaking required. And I'm hoping that the web performance community will meet that challenge and come out and do the experimentation, do the best practices, write the books. I'm sure folks like Ilya will be out there doing his stuff, and yourself, Sergey, and everyone else, and we'll get there. But it's going to take some effort and some discussion amongst the community to get this right. If you're doing RESTful HTTP APIs, I think there's actually a lot to offer in this new protocol. I do a lot of that. It's kind of my hobby, I guess. And because you don't have to think about request overhead so much anymore. You don't have to worry about granularity of APIs as much. Right now when you design an HTTP API, one of the considerations is if I make it really fine-grained, then the protocol becomes really, really chatty, and that's impractical. But with the low request overhead in HTTP 2, that's not nearly as much of a concern. Likewise, a lot of people are going off and doing batch operations for APIs to batch up a lot of different requests into one request. Not necessary anymore unless you need to make that atomic. You need to make that all one operation for semantic reasons. But for efficiency reasons, it's not as necessary, which is great. And again, in your API, you can use headers a lot more and not worry about their overhead so much because you get the header compression, which is cool. So where are we at? What's left? What's next? one of the big issues that we're still nailing down in completeness is, and probably the biggest technical challenge of the whole thing, is merely upgrading, negotiating the new protocol so that you can seamlessly use this thing and not have people notice, any failure or any delays, that it works all the time, or when it does fail, it fails really gracefully. And that's because HTTP is a really widely used protocol. We don't know all the different ways it's used. We don't know all the different implementations, and so it's really hard to make assumptions. And especially when you have all these middle boxes out there doing weird things with HTTP on networks, it's really hard to deploy an evolution of the protocol. So we've taken two approaches. One is for HTTPS URLs, it's relatively simple. There's a new TLS extension called ALPN, and ALPN effectively negotiates what the next protocol is going to be on the wire, the actual application protocol, before you talk a byte of HTTP. And so it's part of the TLS handshake. So that's pretty easy. For HTTP URLs, it's a little more complex. HTTP 1.1 does have this upgrade mechanism defined for it. That was part of the protocol. Roy and the rest of the team foresaw that we'd need to do this one day, and so they included that in the protocol. And we've defined how to use that for HTTP 2. Unfortunately, a lot of implementations don't work well with upgrades. We're not sure how that's going to work on the open internet. And so we've defined another mechanism. It's a hint that goes along with a response to say, here's your response to that request you just made. And by the way, if you want to talk HTTP 2 to me, you can do that on this port over there. And so then you can create another connection and use HTTP 2 on that connection. And that's using that alternative services approach that I talked about before, where you have the ability to inform someone of another place to get things for that origin. Another thing that's still an active topic of discussion is what's called opportunistic encryption. Really, this is just using TLS for HTTP URLs. So in other words, the user experience doesn't change at all. You don't get a lock icon. You don't get any security context changes. It still looks like you're going to a normal vanilla HTTP web page, unencrypted. But under the covers, it is encrypted. It does use TLS. And this is a technique that's used to overcome passive attackers. And passive attackers are things like, the Snowden stuff. Passive attackers are like the Google Street View attack or the Firesheep attack. It's not good against active attackers because in the current proposal for opportunistic encryption, we don't check the server cert. You can use any old cert. The important thing is you're just using encryption. If an active attacker inserts themselves in the connection, they can easily work around that with a downgrade attack, or they can personify the server and get in there. But for the passive attacks, this is a useful technique. And we're not checking the server cert primarily to make it a lot easier to deploy on the server side. If you don't have to have a valid cert, you can just use a self-signed cert. It becomes easy to automatically generate a cert and install it on the server where the administrator doesn't have to get involved. And we're doing this, and we're talking about that this week. It's not an official work item of the working group yet. I suspect it may be. I have to be a little careful in what I say. I suspect it may be because the IETF just published a best current practice document which identifies what we call pervasive monitoring, in other words, the Snowden stuff, as an attack against the core of the internet. And when something is defined in that way, IETF working groups creating new protocols have to demonstrate that they've addressed that threat, that they have mitigated that attack. And so when we take this for publication to the ISG, to the body of area directors that says yay or nay to new protocols, we have to prove that we've done that. And this has been put forth as one way that we can do that. Mozilla is somewhat excited about this. They're implementing this right now. Other folks are not as excited about it. They're concerned about what it means for security on the web. So this is one of the things we'll be talking about this week. Another big topic that's still quite nebulous is the role of proxies in things. As there's this inevitable drive towards encryption. There's a lot more deployment of encryption in TLS than there was even a year or two ago. And that's being driven by a lot of things. But as that happens, network operators are getting more and more concerned because they're used to being able to put boxes in that look at HTTP connections and do certain things, whether it's content filtering at your local school or your prison, or it's a mobile operator who's has to make their cell towers economical, so they want to re-encode video as it goes out to handheld devices, because let's face it, your handheld device doesn't need 1080i or whatever, and the bandwidth is going to kill the economics of how they provide a mobile service cheaply. And so they do a lot of video re-encoding. But when it's encrypted, they can't do that. There are lots of other use cases as well. And so there's a really big discussion happening right now about, there are these stakeholders in an HTTP connection. There's the origin server and their concerns. There's the end user, the client, at the user agent, and their concerns. And then there's the network in between them. And what's the appropriate balance between those parties? And there's an ongoing discussion there, which is, it's not clear where it's going to end up, but that's one of the hot topics in the working group right now. Another topic that comes up often is WebSockets over HTTP2. Simply when you have this multiplex connection available, why not stick WebSockets across it as well? And so some people are proposing we have a protocol extension or another version of the protocol that allows you to do that, to stick a WebSocket semantic across this new connection. Another approach would be to use that server push mechanism to actually kind of synthesize WebSockets using server push and maybe a new browser API. So there's some discussion and some prototyping to happen there as well. One of the kind of the biggest looming discussions is about TCP itself. Once you get rid of these gross inefficiencies in HTTP and make it a fairly reasonable protocol for performance, which is kind of where we're at now, you immediately unmask issues with TCP. And especially around TCP has its own head-of-line blocking phenomenon. It is an ordered delivery protocol. And so if a packet is dropped and you have 15 responses queued up in your buffers on the client side, but one packet from the first response is missing, none of those responses can be delivered to the application. And that's a big problem for performance, especially with a protocol like Speedy and HTTP2. There are other problems with TCP as well, around congestion control, slow start, so forth and so on. And so people have talked more and more about how do we address these issues with TCP. And over the past few years, and especially the past few months, this is becoming a fairly loud conversation. And so there are a lot of different proposals on the table right now. People talk about using SCTP over UDP. SCTP is kind of a telecoms focused multiplex protocol. And the folks who advocate that are like, use our protocol, this is great. TCP minion is a really interesting proposal where you reuse the TCP packet format, the wire format, but you change the semantics on each end to get some really interesting properties out of the protocol, and that gets you through middle boxes really easily. And one of the ones that gets more buzz these days is called Quick, which is a proposal out of a different team at Google, and they are proposing a new, I would characterize it as kind of an HTTP optimized transport-ish protocol over UDP, but it could become HTTP 3, it could become a new transport protocol. It's hard to say what direction it's going to go in, but they're using UDP and building things into it to give it TCP-like semantics-ish, connected multiplex semantics, using things like forward error correction and in transport encryption and lots of cool stuff. It's already in Chrome, and Google's experimenting with it. They've been experimenting with it a while, and I'd expect to hear more about that pretty soon. But that's kind of one of those over-the-horizon discussions we'll be having, I'm sure. So that's all I've got. We do everything in the working group on GitHub. Excuse me. The draft is in GitHub. You can send pull requests if you find anything from a spelling correction to wanting to change drastic parts of the spec. We keep our issues list there. We also have, excuse me, a new FAQ that we put up to answer the most common questions about the effort. We also have a Twitter account that occasionally tweets about stuff we do. And I mentioned before Ilya's Web Perf Crash Course. This presentation's online. I can send a link maybe to Sergey, and you can send it out to folks. That Ilya's presentation is a great one if you want to get up to speed or refresh yourself on core issues in Web Perf. So that's all I've got. Any questions? Yes. So the question's about prioritization and what impact that has on the browser. Studies, no. It's interesting. The browser guys by far are the ones who are pushing prioritization the most because they see the performance impact. They really want to get away from doing all those heuristics about what request to make when, and that's why we've spent so much time designing the prioritization scheme. And so it works, the browser, basically you build a tree, and you say, these are the tree of dependencies that I have in my page load, which the browsers already do. They already have to do that now to figure out what requests they make. And so what they're really doing is serializing that tree and putting it out on the wire and saying this request depends on that one and that one depends on that one, and you can rebuild that tree on the server side. It actually, the burden, if anything, goes to the server side. They have to recreate that tree and do something sensible with it. Now, they don't have to. Ultimately, the server decides which responses it sends in what proportion and when. And it has, it controls what it sends at all times. But if it doesn't pay attention to the browser prioritization that is sent from the client, it better really know what it's doing, because that's really good information out of the browser about what it needs first. But I haven't heard any of the browser guys complaining that it's hard for them or resource intensive for them to implement on their side. There are some concerns from intermediary people about how easy it is for them to translate the priority tree to their forward connections. And actually, our most recent prioritization scheme, I think they're a little bit happier with that because it's easier to do that. So the questions about prioritization so statelessness in HTTP is often mischaracterized. HTTP is a stateless protocol in that you don't have to keep state from one message to the next to evaluate a message. Each message is self-describing. Having said that, servers and browsers do keep a lot of state about connections to manage how that connection behaves overall, and that is continued in HTTP2. The biggest thing we're adding in terms of state in HTTP2 is actually the compression context. You have to keep state about what headers you've seen before on that connection, and there's a described protocol for doing that, and that's actually adding a lot of state. In terms of priorities, you do have to keep a bit of state if you want to respect the full priority tree, but it's pretty minimal. It's contained, where you don't have to keep things much beyond the lifetime of a particular request if it goes out of scope. Right. So each request or each stream on the channel, on the connection, is independent in every way except for really two. One is the header context, and the way that we've specified how headers are serialized on the wire means you always know what your current header context is. And if you have an error state because of a bad implementation or whatever, you tear down the connection. You say, sorry, you messed up, we can't talk anymore. Open a new connection, we'll start again. And that's an implementation error, that's not a protocol error. The other is the priority trees, and if in that case, you basically reroute the tree so it becomes a new root node, and so you lose a little bit of information in terms of relations, somehow, but it's relatively contained, and you can still get useful information about the remaining trees. Yes? Sure. So regarding caching, the question was, how does all this relate to web caching? Server push is the part that does touch caching, because you're logically pushing into the client's cache, and that's a genuinely new thing that's happening. Server push is being able to push something in the cache so you avoid the round trip of waiting for the client to ask for it. If you know that I just sent you some HTML and I know you're about to ask me for the images, for example, I can push the images into your cache to avoid the round trip of you waiting for the response, parsing it, and then sending me those requests. There are lots of other use cases for server push if you want to get a little more creative about it, but that's the main one right there. In every other way, caching operates in exactly the same way. We're not changing the caching model. We just redocumented the caching model from the HTTPbis work that I talked about at the beginning, the revision of RFC 2616, and I was the editor for that section. I feel we really did a good job in that. One of the first things I did was we tore about 10 pages of redundant spec text out, because 2616 said the same thing like 3 different ways for a variety of topics in slightly different ways each time. It was really confusing, and so it's a better description of the HTTP caching model, but HTTP2 doesn't change that at all. There are discussions going on about other revisions to the caching model and perhaps improvements to HTTP caching, but that's independent of the version. If we do that, it should be able to be used in HTTP1 just as well as in HTTP2. And the second question, sorry, was prioritization of connections. So in terms of use of TCP connections, the stated intent of the browsers is to use one TCP connection per origin. So if your website all loads from one origin, it should be one connection. There may be circumstances where it decides to use another one, but the common case would be one. If you're using multiple origins, it'll use one per, and it'll operate just like it does now. There's discussion about what we call connection coalescing in terms of being able to put multiple origins on the same connection. So that you can get the benefits of using one connection to lots of different sites if you have third-party widgets or you have a sharding going on and you want to coalesce those. We're going to talk about that this week. It's not clear exactly where that's going to go. It's not hard at the HTTP layer to do that, but with TLS it becomes really, really tricky because TLS has this baked-in notion that you're talking to one host name, not to 5 or whatever. So we'll see how that goes. Excuse me. In terms of your application and prioritization, we don't specify anything because we don't specify HTTP APIs. I would imagine that different HTTP toolkits are going to have different approaches to that. Some of them might use heuristics to decide, okay, this is how I'm going to do prioritization, or they might give you knobs to turn to do it. There's already discussion in some W3C contexts in the Web Performance Working Group in a couple of places about prioritization APIs where you're prioritizing one request over another for different resources or for XML HTTP requests. So that could show up there as well. We'll see. Sure. So Google, the question was Google, what are they up to? The way that Google thinks about Speedy and HTTP2, as far as I can tell, is they consider Speedy to be kind of a test bed for experimentation, and they feed those experiments into us. So they decide, they have an idea, they test it in Speedy, and if it works out well, they'll say, here, let's try this. And so they've kept Speedy open as a platform for that. They did Speedy 2, that was the original proposal, and that was the place where we forked from them and said, this is HTTP2. They did Speedy 3 after that, which was some revisions based on some severe problems they found in Speedy 2. And then 3.1 to fix some issues there. And then for the longest time, they've been kind of sitting on 3.1, and they've been saying Speedy 4 is coming. And the reason is that Speedy 4 is HTTP2. They've actually taken the HTTP2 doc and fed that in as the basis, and then they do deltas on top of that. And they haven't shipped it for the longest time. Personally, I suspect they're doing that because they just want to put pressure on us to make sure we actually ship HTTP2. They don't want to actually fight with, it would be bad if we had diverging efforts here. When we started this effort, they were very clear that they wanted to, do the right thing by the community and make it a standard, not just make it a proprietary protocol. Firefox felt that way very strongly. And in fact, the original Google team, Mike Belshie, who's left Google since, he's still active, although he can't travel as much anymore because he's doing a startup. Roberto Peon, who was the guy who at that time was responsible for the Google front-end servers and implementing it on that side, he's still highly active in the effort. Will Chen is one of the lead Chrome guys who's been involved since day one, and he's one of our most active participants on both Speedy and HTTP2. And Hassan Khalil, again, on the server side, very active participant in both Speedy and HTTP2. So it's a parallel path. The browsers have said pretty publicly that they're going to end of life Speedy as soon as we ship, and they're aggressively end of lifing each version of Speedy so that it doesn't become a de facto standard, because that's not a good outcome. Right. So the question was about Apple's announcement of Speedy support. That's a good question. I haven't had a chance to talk to them. I went and gave pretty much this talk to them, I guess, I don't know, a year ago, something like that. And they were very receptive, so they're aware of what we're doing. We do actually have one Apple engineer showing up, but he's not representing their stack. He's representing Apache Traffic Server. They're aware of it. I'm hoping I'm going to be able to talk to them soon and clarify what their position is. I'm hoping when they say Speedy, they really mean Speedy/HTTP2. It would be a really bad situation if 3 of the browser vendors out there are on HTTP2 and they've end-of-life Speedy because it was just a transitional thing, and Apple were to announce Speedy as a long-term product decision for them. That's not good for anybody, really. But we'll see. Hopefully we'll get some clarity pretty soon. The question's about tool support and how it affects things like analysis of performance and so forth. Yeah, I think it is going to have some effects. You're going to have to think differently about a page load and how it uses HTTP. And there will be different factors to performance. because we've been moving so fast with the protocol, we haven't settled down enough where people can take the time and put the investment in to write the tooling. I'm hoping that once things settle down and we say this is where we're going to put the stake in the ground, we'll get more tooling out there. One of the biggest problems I think is just visualizing, letting people visualize what this looks like on the wire, so they can debug it and think about how it's behaving and optimize it. That's a hard problem that hasn't been solved yet, and we'll need to get some people working on that. But once the protocol settles down, that becomes a lot easier. Yeah. Sure. So the question was, has there been any discussion of peer-to-peer and the advantages that has in terms of bandwidth conservation? Yeah, that comes up in a couple of different ways. There's a research activity in the IETF right now, or the IRTF, the research arm of the IETF, about what some people call content-centric networking. And there are a lot of different names for it, but it's kind of, when we identify something by its hash and then, peer and do interesting stuff there. And it's a fairly radical change to how you think about the internet. Whether or not that's going to take off is anybody's guess right now, but there are a lot of really smart people working on it. More concretely, when we talk about more encryption on the internet and more encryption on the web, one of the things that falls by the wayside is web caching. It's fine if you have a CDN, for example, but if you're a village in Africa and you're using a web cache to make your really tiny little dial-up connection to the rest of the world viable so that local farmers can do whatever they need to do or what have you, and it's not good when everyone starts using encryption. And so there's been a lot of discussion about what can be done to improve that situation. One of the answers that comes up fairly regularly is, well, what if we had kind of a peer-to-peer caching protocol where you could advertise what's in your cache to people on your network and you could share that? The problem that always comes up when you talk about any kind of these peer-to-peer scenarios is privacy. When you're using a peer-to-peer protocol to discover web resources, you're effectively advertising what you're browsing to everyone around you. And yes, you can do things like use hashes or find some cryptographic means, but at the end of the day, if you need to be able to look it up in a cache, somebody else can figure out what that content is too. And over the years, and especially recently, the privacy community has become very sensitive to any kind of leak of information, because what may be completely innocent in one context can get somebody killed in another context, depending on, if you're, one of the examples that's been brought up in a lot of the conversations I'm in is, if you're a gay teenager in Nigeria and you're surfing for resources in the gay and lesbian community, that can get you killed. And so peer-to-peer becomes a little bit weird in that kind of discussion. From a technical standpoint, I'd love to see it. I think it's quite interesting, but it's got a lot of downsides too. Yes. So the question was, is there a race where the server can be pushing something as the client is requesting it and they effectively cross on the wire? You can mitigate that. There's a mechanism called push promise, where you say, I am going to, as the server, I'm about to push this to you. Be aware and be ready to receive this thing. It gives the client a chance to reserve resources for that in the stream accounting, but also to gives them a chance to cancel it if they already have it. It is, but it's initiated by the server. So in Speedy and HB2, the odd number streams are the ones initiated by the clients, and the even numbered streams are the ones initiated by the server. So the server's creating a new stream and saying, here's something I'm pushing at you, here's something I'm pushing at you. And so the server, the client can cancel that. Even if you do get a race and it ends up requesting at the same time, worst case, it's redundant. Once the server realizes or the client realizes that there's a duplicate request inflow, they can cancel that, and no foul. Mm-hmm. So the question is, what are the bottlenecks in HTTP2? Once we have the multiplexing, for example. So yeah, it's not numbers of requests made, and it's not as much header sizes. You can certainly blow out the header sizes if you really try. The header compression relies on that similarity that we see in the common case. Resource consumption is very different in HTTP2. I think, for example, people doing web application firewalls are going to have a good rethink about how they do their business to deal with this protocol. The bottlenecks really do shift down to TCP. It becomes much more about TCP connections, and in some ways it's better because you're using less TCP connections for page load, but you might be keeping those connections open for longer. So it's just different. I think those underlying problems in TCP are the next set of bottlenecks to get over. Yeah. Yes. What are the timelines? So that's something we're going to talk about this week. I sent an email to the list a couple weeks ago. From the discussions I've had in the working group with the implementers and kind of the tenor of the conversation, I think we're at a point now where we really can shut down and then say this is the one we're going to do what we call a working group last call on. And that is where the working group says to itself, we think we're done. If anybody has any more issues, raise them now. Review this document. And then once we're done that, we send it forward to the IESG, which is the body that makes decisions about what to publish as RFCs. They go through an IETF-wide IETF last call. That takes a little while. Then they put it on a teleconference and talk about that. And then once they do that, it gets sent to the RFC editor, assuming it passes, and they take a while to publish it. So in a best-case scenario, if everything goes smoothly in that, I think we'd have an RFC by the end of the year, maybe before, maybe like November-ish. If significant issues come up or we have really intractable conversations that we get bogged down in, that can easily blow out. And so it just depends on what happens between now and then. But that's kind of probably the most reasonable best-case scenario. I know the implementers are very keen to get stuff out there. They've talked about shipping this code pretty much as soon as possible. They really want to see it in the browsers right away. I won't say exactly when because I don't want to make announcements for them, but they're thinking very aggressively. The application level shouldn't have to change. I think, like I said before, it may be that there are new knobs and tweaks you can make on the APIs, but it's not like you fundamentally have to re-engineer your application to use the new protocol. To get the most out of it, you might have to make some small changes, but debugging. Both Chrome and Firefox actually have a mode where you can start up the browser with a command line, not a command line, with an environment variable, which tells it to log its pre-master key to a file. And then you can feed that file into, for example, Wireshark and decrypt stuff on the fly. There's a link that explains how to do it in the HTTP2 FAQ on the GitHub site, at the very bottom of the FAQ, I think. So it is possible. There are other ways you can do it. You can install your own CA and then man in the middle yourself. It's not ideal, but hopefully both the in-browser tools as well as stuff like that will make it easier. Not great, but possible.